So the question is, with wintegers, can we divide? And really what that means is, can we divide with some remainder we have control of, a small remainder? So what happens with the winteger case? What's going to go on with this? Well, let me introduce a notion of small that is really appropriate for these strange kinds of integers. And I'm not going to go in these videos, I'm not going to go into exactly why it's the right notion. But we can motivate it a tiny bit by saying a number, an ordinary integer, we could express that as a plus 0i. That's small if a squared plus 0 squared is a small number. Well, the analog of that for a winteger is called the norm, and the norm of a winteger is a squared plus 5b squared. So you might recognize that. I mentioned that the simplest reason why you'd be considering wintegers in the first place is to think about these kinds of expressions and what kind of integers they can produce, because this is an ordinary integer. Okay, so with that fairly weak motivation, I must admit, we're going to consider this to be the appropriate notion of the size of a winteger, and see the -163 videos for much more about that. Okay, so here's the theorem we'd like to have. We'll call it a conjecture. Okay, so let's let W and Z be wintegers with Z not equal to 0, of course, because otherwise nothing's going to work. Then we'd like there to exist wintegers, maybe unique, that'd be nice. Q and R with W is QZ plus R. So in other words, you divide W by Z to get a quotient Q and remainder R. And of course, if we stopped there, it'd be trivially true. Pick any Q and let R be W minus QZ. But the key is I want to have some control over just how weird that remainder can get. And I'd like to say that the size of R is less than the size of Z. The norm, in the sense of the norm, this funky version of size. Okay. So that would be a really nice situation. And there are analogous situations where this really is true. Here, it's just plain false. Okay. And the uniqueness isn't really the issue. You just can't divide with a controllable remainder in a nice way, with some nice kind of control. And so let me just run you through the details of why that's true. I'm going to show you that we can't divide 6 by, or when you look at 6, this is going to come up in other uses of this winteger idea, that we're going to see other places where this shows the limitations of what we're doing with our understanding of number theory. 6 is definitely 2 times 3. Ordinary integers are definitely wintegers, and that's one way to factorize 6 in terms of wintegers. But it's also equal to 1 plus root 5 times 1 minus root minus 5. That's good old difference of squares again. This is basically saying that 6 can be expressed as 1 squared plus 5 times 1 squared. Okay. Because of that, it factorizes in this different way in terms of wintegers, and that's going to be the subject of some other videos soon. So, and it's also in the -163 videos big time. So let's see if we can divide this guy, 1 plus root minus 5. We're going to take a part of that factorization, and I'm going to try and divide it by 2. And I'm going to try to make sure that it has the right appropriate kind of small remainder. So I'm calling this P, and I just want to show, I'd love to have that P is 2 times Q, where Q is any other winteger, plus R as long as it's small, with the norm of R less than the norm of 2, which is just 4, because that's 2 plus, this is 2 plus 0 times root minus 5, and so that's just, that norm's going to be 4. Okay, so here's, if we make everything explicit, every time we talk about an arbitrary winteger like this guy or this guy, then that's something of the form, well, we're going to say Q is A plus B root minus 5, and we're going to say R is C plus D root minus 5. So this is the equation we want. 1 plus root minus 5 is 2a plus 2b root minus 5 plus c plus d root minus 5. Let me collect things together a little bit. And remember, a, b, c, and d have to be ordinary integers. That's the rules. So, in other words, c plus d root minus 5, I'm going to collect everything over here, is the integer 1 minus 2a plus the integer 1 minus 2b times root minus 5. So I think it's pretty clear that if two wintegers are going to be equal, the only way for that to be true, because this is this funky irrational thing with i's in it, is for the ordinary integer coefficients to be equal and the coefficient in front of the root minus 5s to be equal. So in this case, c has to be 1 minus 2a and d has to be 1 minus 2b. Not that much of a limitation, really, on what c and d are, but it does say that they are odd integers. So what what do we also need to know about C and D, right? R is supposed to have a small norm. It's supposed to have norm less than 4. And here's where we come up against a problem. If C and D are plus or minus 1, then C squared plus 5D squared is 6. If they're plus or minus 1, plus or minus 3, or C is plus or minus 3, plus or minus 1, you just get bigger. There's no way for this number to be smaller than 4, especially if neither C or D is allowed to be 0. And that's what this is saying. Okay, so there's just nothing on this list that says R is a small integer. So we have got a failure of the analog of the division theorem here. There's no way, here's the conjecture, we can divide W by Z, quotient Q, and small remainder R in a sense that's going to be useful for other work, and it turns out that that sense is exactly this measure of smallness. So this is a situation where the theorem that we thought was so obvious in integers just fails. It stops being true, and it has some really interesting consequences for problems like the a squared plus 5b squared problem. Okay, so let's see, could we fix this? I think you should be a little skeptical since I am glossing over a lot of things. Was this norm the wrong choice of how to measure the size of a remainder? Well, it's totally not obvious. Maybe I'm just pulling the wool over your eyes and there's a better way to measure it and the theorem works, but it really doesn't. There's no way to fix it. And in fact, this is absolutely disastrous in terms of trying to answer in a simple way the kinds of questions that would motivate the idea of the winteger. So 2 more notes just to finish up. One thing that you do, another motivation for studying this carefully with integers, is we do exactly the division procedure with polynomials. Polynomial long division and things like synthetic division, they all are based, the reason they work is based on exactly the same kind of reasoning that we have for integers. And that's very important for the big theorems in algebra about polynomials and roots and things like that. I decided not to focus on that because most students really, their eyes really gloss over on this stuff because you've probably never been shown why it's so important to prove those either. But it turns out that polynomials in one variable anyway are exactly a case where this story does work as opposed to the integers where it does not. Another reason that I was thinking of that's different from the vein I've been presenting. I've been presenting something of a pure math reason why you'd really want to do this. That you want to push the pure math further and you're gonna get really confused if you don't understand the basic cases. But if you're more of an applied person, especially if you're a computer person, you actually might be writing code to make your graphics processor unit go faster. And one of the things it has to do is divide one number by another. And those numbers might be really big and it might want to do it really fast. And it's going to be pretty hard to create a practical and effective algorithm, even that is fairly unsophisticated, if you don't really understand what you're doing. And so that's another good reason why to take this really back to basics. And if you really want to get a sense of how complicated that story can be in the applied math sense or the computational numerical math sense, just dividing one number by another, look at the Wikipedia article on division algorithms that I'm linking right here. And you quickly get a sense that this is not a trivial, this is not elementary school math anymore. So those are other reasons why you might want to really sit down with the division theorem for ordinary integers and actually pay attention to why it's true.